Cool. Hello, hello. Check one, check two. Recording's going? Yep. Screen sharing. You can hear me. Perfect. All right. Hello, welcome. Week 5 of the data science bootcamp. Sorry for missing last week. I know Karen did a great job. I rewatched most of the lecture, and summarized it. So yeah, great job talking about SQL and everything. I was on a work trip all last week. I was actually out at spring training, which was a lot of fun. So down in kind of Arizona, catching up with a bunch of the teams I know down there. But yeah, last week all about databases. So there are two big ideas I wanted to get out of week 4, which I can actually pull up in my GitHub notes. So yeah, if you're ever curious, I do post. I have like a in my GitHub for the course. I do break down like some big themes from the week, and then I also generate notes before my lecture, which I call like this big ideas.pdf or whatever. So if you're ever curious about like my lecture notes or things I want to make sure I hit on or cover, you can always creep on my GitHub stuff, and it's always there. Yeah, there are two big things I wanted you to think about with databases. The first is like why databases exist and kind of a little bit of the history of databases and how they kind of have had to adapt and change to support modern data problems. So just a big recap. Databases exist to provide a single source of truth to multiple like readers or solutions, right? Or consumers, if you will. So if you just have a million different copies of an Excel workbook, we've all done it. You have Excel final copy V6 copy V7 final. Like if we all have those smatterings of like workbooks and data sets floating around, right? Then how do we know what is the real data within it? And especially when we have multiple consumers, whether it's applications, BI tools, analysts, data scientists, if we have multiple people trying to access this data, it needs to be trustworthy. So that's why we came up with this idea of relational database systems. So you're going to hear this called RDBMS, relational database management systems. So your very first ones came out in the 70s. This is your Oracles, your SQL servers of the world. And the big idea behind it is trust. That's why you have relational databases with strong controls, such as type enforcement, right? This is going to be a column that is going to be a decimal. This is a column that will be a date. This is a column that will be text, right? That is enforcement, which guarantees trust. And then relationships, primary and foreign keys, unique representations of the data. This row is guaranteed to only be Grayson, right? This row is only going to represent Brian, and here's my ID to represent that. So you have strong controls around identity, relationships between the tables, how the tables relate to each other, as well as the data types itself. I think Karen showed an ERD, an entity relationship diagram. Hopefully I don't just, yeah, there we go. And again, this is kind of what we were all operating off of. Even when I first started in data 15, 20 years ago, like it was still all just relationship diagrams like this. Like here's my table, here's how it connects to my other tables. Let's find a good one. Here we go. Here's my table tickets. Here's how it connects to my other ones. Here's going to be the guaranteed schema. Here's going to be my relational ways that this table comes in. And even though it looks kind of messy, it provided trust, right? It provided trust inside of that single source of truth. And this is why RDBMS is still core of many enterprise applications today, is that we need that trust, right? And as you'll see how data has evolved, I'll be real quick on it so we can dive into week 5. But where kind of the database evolved was when we went into the 70s and 80s was all Oracle, Microsoft SQL Server on-prem. In the 90s, we got to open source databases. Oracle and SQL Server, very expensive. You're paying them really expensive fees in terms of licensing. So in the 90s, we get MySQL and Postgres, which is what you used in week 4. I think you used both MySQL and maybe a little bit of Postgres. So those are open source versions of this, and it kind of democratized who could use databases, right? Almost anyone now, if you wanted to spin up a trustworthy application system or enterprise data system, you can do it now on open source technologies. Then, of course, in the 90s and the early 2000s, you kind of get the dot-com boom, right? You have the rise of the internet, the rise of what we start calling big data. And so now you have data sets that are coming in that are not trustworthy. This was kind of the big change, right? If the analogy I do for this is like on Twitter or X, you can specify your location to be wherever. So I'm tweeting this from the Arctic Circle from my Samsung smart fridge. Obviously, I'm just making that up. But that's data that's coming into your system, right? And so now if you're having data that's a lot messier coming from this whole internet or even Internet of Things, we need ways to store that in a more efficient way. So this came with NoSQL. So NoSQL came out in the early 2000s. The most popular one is called MongoDB. Uh, and if you look for some of its history, it's like, yeah, 2007. There you go. And the idea was we want to be flexible, right? I don't want to always have to have data that has to conform to a schema. I don't want to always have data that has to conform to these relationships. And so that's kind of the purpose of a NoSQL is how do we provide flexibility to a database? But on the con side, by introducing that flexibility, you lose trust, right? You lose the trust of a relational database management system. And so that's why you ended up with some architectures where data came into NoSQL first, and then it was extracted and cleaned, and then loaded into a relational database system down the line. So you had like two landing areas. And then this kind of became its own cloud paradigm of a data lake and a data warehouse. So a data lake and a data warehouse is just big data architecture on the cloud. A data lake is where anything can be dropped. No schema is required, no nothing. We're just going to drop this into a cloud storage location, or it could be a NoSQL location. Then we're going to clean it up and push this data out onto a much more queryable format known as a data warehouse. The difference between a data warehouse and a RDBMS like Oracle or SQL Server is just scale. With SQL Server, Oracle, Postgres, I have to install it on a single laptop, on a single computer, on a single server. It has to scale vertically, right? If I want a bigger database, I have to get a bigger computer, right? We install Postgres and scale it up vertically. With cloud warehouses, we scale horizontally. So what that means is that I can have multiple computers and multiple servers all working together to power my database. And that's only possible with cloud technologies. So that's why you don't have an on-prem BigQuery or an on-prem Snowflake, right? They just don't exist because they require the flexibility of that horizontal scaling that cloud provides. So that kind of got brings us to the 2010s with this idea of a lake and a warehouse. And then kind of at the end of the 2010s, early 2020s, you kind of get this idea of a lake house on kind of data mesh like systems. So lake house is kind of the more modern paradigm. It's where I work at Databricks and other ones like Snowflake, AWS, they've all kind of bought into it as well. So the idea instead of having your lake be one thing and your warehouse be another, you end up, if you do have that architecture, you end up with brittle pipelines that has to move data from one place to another. You also lose your single source of truth because now how do I know if I have to go to the lake or the warehouse or if the warehouse is everything that's needed there, etc. So the idea of a lake house is unify everything. And oh, the last bit of this was let's say you have unstructured data. So you have documents, PDFs, text, right? That doesn't fit into a classic idea of a data warehouse or even a relational database system. All this text and unstructured data still needs to be consumed, though, especially in the age of AI. So a lake house says you can definitely have just unify everything, have all of your unstructured data in the lake, have your structured data in the warehouse, but have it all be governable under one roof, have your pipelines still be defined under one roof, provide that single source of truth, and provide that availability to AI tools and AI agents that need to consume them. That's kind of the big idea of a lake house. And then you may hear kind of data mesh thrown around now. Data mesh was a big thing for a hot minute and then kind of faded out of the mainstream a couple years ago. The data mesh is kind of like, let's say that you work for a large company, and this company has a finance team, an R&D team, a product team, and like an accounting team. So what the data mesh says is, sure, each of those independent business units are going to have their own data sets and data platforms, but there should still be some overlap between them. Maybe something that R&D does should be shared back with finance or accounting, or maybe definitely finance and accounting should have some form of collaboration on their data sets, right? Even when I worked for a baseball team, I worked on the front office, so I worked on acquiring players and setting lineups and stuff. But we also had the business side, which is all on fan engagement. And we have two business units. One makes the team, one deals with fans. And we were completely isolated. But it turned out we were ingesting the same data sets and just had two pipelines running in two different ecosystems to do this. And it's like, why are we doing that when we could have my pipeline be the source of truth, and then I share it to the business side to just consume. So that's kind of the idea of a data mesh, is how do we start meshing together across business units, different kind of data platforms, whether it's like a lake houses or just different warehouses, etc. So kind of interesting. There's still a strong place for RDBMS, mostly in terms of powering applications or BI tools. It's always going to be faster going to this is called OLTP. Yeah, this it's dumb. Like there's two RDBMS and OLTP. I hear LTP a lot more these days, but these are the same thing, right? Online transaction processing occurs on top of RDBMS, right? So RDBMS supports OLTP. So OLTP is always going to be faster than OLAP. And there's more acronyms for you. This is an interview question for Databricks, by the way. What's the difference between OLTP and OLAP? OLAP is going to be your data warehousing. So your online analytical processing. How do we query against data warehouses? So it's always faster to go to a RDBMS than it is to go to a warehouse. So if I have like an application like Amazon.com or something, if I'm going to be power or Walmart, whatever, if I'm powering that application and I want to be fast for my users, still needs to have a relational database structure behind the scenes to act as its OLTP layer. But OLAP is much more useful for storing all of your data, right? Historical data, large data, data mining, right? This really, really big kind of data warehousing type thing. You never really want a data warehouse to power an application. Think about how slow Wordle will be if it has to go query Snowflake every time just to pull in the latest like word of the day or something. So definitely good ideas to know. And the last part of this is why SQL. All of this databases from SQL Server, Oracle, all the way to Snowflake and Databricks and BigQuery, they all use SQL. Just a different flavor of SQL under the hood. Whether it's T-SQL on SQL Server, SnowSQL, BQ-SQL, DB-SQL, whatever, they're all still the same at the end of the day. So if you know how to write any SQL, you'll be able to write all the SQL, is kind of how we talk about it. So that was big idea one from last week. What's the history of databases? Why databases matter? The evolution of databases, and then the types of SQL that you will write, like whether you're creating tables, modifying tables, or then querying tables with analytical statements, like your group bys, your aggregations, your time functions, all that jazz. So just kind of what does SQL look like? And then finally, the most important stuff, the second half of week four was how do we use databases with kind of as a data science workflow. And in this case, you have two typical workflows. The first is your database is a source. So it's simply, I'm going to query from my database to bring in my single source of truth into my Jupyter notebook, read it into a Pandas data frame, do whatever I need to do, make my model, make my visualization, call it a day. The second workflow is as a destination. I'm going to be writing to a database as part of a workflow. Typically, maybe that's the second half of an ETL, extract, transform, load. Extract from API or web scraping, like we did in week three, clean it up in Pandas, your transform layer, and then load it out, load it, push it to a destination of a database so that the rest of my consumers can access it as the single source of truth. So how do we write and push data to a database for maybe our analysts down the line? So I think we mostly looked at the first version of this in the labs where we read data from, well, we did a little bit of both. You actually read data from a CSV from a cloud location, wrote it to a table in SQLite, and then read from that table in a downstream workflow. So you kind of did both, practicing that ETL, extract, transform, load to a database, and then query from that database and do your analytical processing downstream. So fun week, fun week. We're not going to do too much more with databases in the boot camp itself. This week is obviously all about pandas and intro to predictive modeling, and then we're going to get into some visualization and then machine learning before we wrap it out. But I do want you to understand kind of where databases and SQL fit into a data science workload, as it is really important. Yeah, big word for 2020. So for 2025, the big word was all about like data governance. And you had kind of this idea of like the war of the data catalog. It was so dumb. It wasn't even really a war of catalogs and stuff. This was 2025 problem though. So that this idea was, let's say that you do have a data warehouse and a data lake and a data RDBMS system, right? How do we make sure that everything is governed correctly, right? I don't want intern Bob to be able to log in and delete all my production tables. So the idea with having a catalog is that we can discover, manage, and govern all your data, having a dynamic like inventory of everything in your data estate. And it can also be pushed into AI tools and things like that. So, yeah, the catalog wars. Oh my God, this was so dumb. 2024 and 2025. Anyway, that's so dumb. I may put a couple of these blogs in just because it was there, they cracked me up. Uh, begun the catalog wars had. Yeah, this was my life for like a hot minute. Anyway, where things have gone into this year, 2026, the big word going around is interoperability or zero copy is what you may hear. So this is the idea that again, I have all my data in my data estate, but I want it accessible to all of my data systems. Why should I have data in BigQuery and Snowflake and have to have pipelines copying and keeping them refreshed, right? Or even with your OLTP layer, your Postgres. Why do I have to copy data out of my warehouse and put it into Postgres, right? Like that's super annoying. So all the big companies these days, well, I started with Salesforce. They have their own, they call it a data cloud, and you'll see they have like a zero copy data guide now, which is basically instead of having to copy data out of Salesforce into your own system, you can just read it directly from their engine, basically. As soon as Salesforce did this, Workday announced a zero copy data cloud. Uh, literally, this was like back in the fall. And then all the other big names in the space are talking about zero copy. So like how does Databricks support zero copy with Delta sharing and creating access to OneLake and here you go, like implementing zero copy architectures and stuff. So this can mostly be done with tools like modern data formats such as Iceberg Delta and like Delta sharing and things like that. But just it's something important to know, right? Everyone's tired of having to replicate data across your data systems. And so using interoperability and zero copy, you get better single source of truth that powers all of your downstream applications. So this is kind of where the modern data estate has gotten to in 2026. And again, this is my life is data engineering, data platforms, and kind of data architectures. So we can talk about this in the future as well. On databases, week four stuff, fun, at least something interesting. Hopefully you weren't just like select star from table. That's great. But the point is way bigger than that, right? Why do databases exist? How have they evolved over time? How do they support big data architectures? And how do they specifically support data scientists, right? And again, like in the real world, You'll have data engineers and data scientists, but in this class, we're operating as both, right? You need to understand how the full ecosystem works of engineering data as well as sciencing on top of it. All right, cool. I'm going to pivot over to module five. Let me double check the canvas is still down. Oh, we're back up. Lovely. Hopefully we're back up. Cool. So I can actually live code some of the notebooks here. So for module five, the big idea of where we moved into, this is a huge week, module five. So definitely don't feel bad if you feel like overwhelmed by this week. It's a crazy week. So it's kind of split into two halves again, kind of similar to week four. So the first half of module five is all about exploratory data analysis, EDA, right? That's a huge part of being a data scientist, especially in the modeling phase. We need to understand our data to be able to use it to make predictions about the world around us. Or sometimes we just want to explore the data just to understand patterns and see what we can do or recommend based off of the patterns that we identify. So to do EDA requires a lot of pre-processing and cleaning of the data, as well as visualization. And we'll have a whole unit on visualization coming up, I think, in week six. Yeah, week six is all visualization. So that's how this is kind of tied together. The visualizations are part of EDA. So don't feel like you have to be like totally like understanding everything that's going on with the cleaning of data and exploring that data, etc. It's kind of a soft introduction. But really, what we want you to understand is how to use pandas to clean and pre-process data. And then the second half of module five is about model building. We're introducing you to machine learning via linear models. So this is how typically all machine learning classes start, is kind of just with your line of best fit, draw your rise over run or whatever on your little Excel scatter plot and call it a day. And that is machine learning. Linear modeling is machine learning. So that's going to be the second half. What does it mean to build a model? What does it mean to be a linear model? What does it mean to understand the model life cycle? So again, getting data, cleaning data, training a model, evaluating the model, right? Again, this is a soft introduction as well here because in week seven and eight, week seven, we're going to dive back into linear models and machine learning, and week eight is also all machine learning. So we got 2 more weeks on this as well. So think of week five as like a softer introduction to the entire life cycle, with week six being more deep in EDA and visualization, and then week seven and eight being more deep in the machine learning life cycle aspect. So yeah, big takeaways for week five. What does it mean to do EDA? Why does EDA matter? How do you do data wrangling? What are some common data wrangling techniques? So missing values, date time and data form, data types, normalization, binning, feature engineering, all that good stuff. Again, if you've already done week five, this is you should know all of these already. EDA, which again we'll go deeper into next week, looking for correlations mostly. And then note if you do have a correlation, how do we build a model to kind of turn that correlation into a predictive engine? What is linear modeling? How do we evaluate models? And kind of what are different libraries that we're going to use here? So that's kind of the big idea. And I'm going to hit on all of those over the next 45 minutes or so. I got 3 notebooks that I want to do, and they should all be fairly quick. But you both kind of understand the big idea for week five. How do we go from data from my database or from source, pre-process it, clean it up, look at it, and find patterns, and then build a model off of those patterns? Yeah, I guess I should just also just say that at a high level. At the end of the day, all that machine learning or predictive modeling is trying to do is take patterns in the data set and use those patterns to kind of make a prediction. It's never something just like out of the blue. It always finds patterns, which is going to be like a correlation. So let's get after it. Let's start with some of the pre-processing. So the first lab I want to do is the pre-processing lab, which is, I think, 5.3, the second one in 5.3. So 5.3.3.2 here. So the practice data wrangling and then the practice model development and evaluation. These are all pretty good ones. And then the keynote is going to be, I think, the house sales in Seattle, which is a fun activity as well. We're connected. Let's go to clear output of all cells and let's start going. All right. So with data wrangling, yeah, with data wrangling, there's typically, yeah, let me get the data and then we'll walk through kind of what we really typically need to do here because I'm going to add some notes to this notebook. So all we're doing, we're just grabbing data. I think it's laptop pricing data is kind of what we're going to be pulling here. Let's grab the data sets. Boom. Uh-oh. Why didn't we like it? Try that. Nope. What is happening? Laptops.csv. It's odd. Host is unreachable. Must be the what? There is my CSV.
There's a bad line in the CSV file.
Is there?
Yeah, so if you do the, what is it? In PD, you can skip a bad line. Let me look at it real quick. I have it here.
Am I
It's about 239 or so.
dumb? Let's see if I can just upload.
Anyway, hold on. Let me find it again. There's just something you can put
The
in the read
no, I don't
CSV.
know what's yeah, I got it. I just uploaded the one from when I downloaded it from GitHub.
Okay, yeah, that might work too. But I was just gonna
Yeah, I
say
don't
this
know
is,
why. Someone
I had
changed it.
that
Yep.
problem just this morning on it, and
Okay. Yeah, post it in chat when you got it.
yeah.
Anyway, so here's the data frame, and let's look at the df.head. So there's a few things I want to look at. Whenever I have a data frame like this, there's always going to be some data cleaning we're always going to have to do. So I always start with df.info. And the three things I'm looking for here are going to be missing values, data types, and column names or column names, I guess. So with every single data set you're ever going to work with, these are always the things you're going to start with. So let's start with missing values. We have 238 rows here, but I do see that we have missing values. Screen size centimeter is missing 4 rows. Weight kilograms is missing 5 rows. So we have null values in screen size and in weight. And maybe a little sad face because this means we have to do work. Next one I check is data types. So these data types all look pretty good to me. We all have mostly numeric. This is the one other thing to look at when we get into the second half of pre-processing. When we build a predictive model or any machine learning model, it has to be built off of numbers. Even your modern ChatGPTs and Geminis, they're built off of matrices of numbers. And there's actually techniques to convert text into numbers. It's called encoding. That's what we're going to do a little bit later here. But in this case, we only have two text objects, manufacturer and screen. And if I just do a quick check, yep, those are both going to be text. All the rest are numbers. We don't have any date times. So data types look good to me. And it looks like we could maybe round a few of these. So they wanted to round some screen size. I'm not really into rounding usually. I like keeping my data types
Why
raw.
is everything erroring out now? Oh no, don't pay attention.
Yeah, sorry, Karen. Cool. And the last one is the column name. So the column names, there are some weird ones here. we can see that column one, which looks like to be our ID column or index, does not have a real name. So we're missing a name. And then the other one I look for are weird foreign characters or spaces. If there's a space or foreign character in the column name, I like to remove those as well. Usually I also like to make them lowercase and all that stuff. But in this case, I'm not going to do that. So there's some work that we have to do on this data set. We have to fill in the missing values, and we probably need to deal with this column name. All right. So let's go to task one. We're going to look for missing data. Again, this is a loop to look for missing data. To me, this is excessive. You could just do a df.info and see all of this. df.info is my favorite pandas function, by the way. So we should see the same thing. We have two missing value columns, screen size and weight. And how we're going to do this, when we deal with missing values, you have two options. The first is going to be something known as imputation. Imputation is where you fill in the missing value with another number. The other one is just drop. You just drop the row or drop the column that has the missing values. Usually, the rule of thumb is something like if you only have like 20 to 30% of the rows, then you probably should drop the column, right? If you don't have enough data to impute, then you drop. So, also for me, like if it's less than 5%, I usually drop the rows. So, I guess my rule of thumb would be less than 5% of rows are null, drop the rows. If you have 25 to 30% of the column, uh, if you have like over 50% of the column is null, might want to drop the column. So dropping the column or the row is always easier than imputing. So it's also known as the easy way out. Imputation is a lot harder. That's where we fill in the value. Typically, this is done with either the mean, median, or mode, mode being the most frequent. So in this case, we're going to fill in the missing value with the average. So let's look at kind of what we're doing here. These are the five missing rows. These are the five rows that are missing a weight. And what we're going to do here is we're going to grab the mean of it. So let's actually just figure out what the mean is of the weight column. So excluding those nulls, this as type float is irrelevant because it's already a float. The average weight of a laptop is 1.8 kilograms. So that's all we're going to do here. We're going to replace these five nans with this 186. And then in this case, all I wanted to show here was we have five rows out of 238 that are missing, which is like 2%. So I would just, you could just drop these rows as well, right? Because 2% meets my 5% rule. So you could just drop the rows if you wanted to. So I'll put as a comment, dropping them is probably fine. Anyway, here's how we're going to do the imputation. We're going to grab the average weight, and then we're going to call this line. We're going to grab the weight column, and we're going to replace the null values with the average weight. And if we do this correctly, we should see that we have no more is null values. And if I go find, I'm just going to go find this row right here, 29, df.iloc 29. We see the weight kilogram is 1862232, which should be our average weight. So we just replace the null value with it. Cool. So that's mean imputation. If your data is skewed, then you may want to use the median instead of the mean. And I probably should have calculated that as well, just for completeness sake here. So my median is also 1.862232. So since they're basically the same, it doesn't matter which one I use here. Cool. The other way to do it is to use the most frequent value, otherwise known as the mode. And so if we look at screen size, we see that in this case, there is a little bit of skew here. My mean is lower than my median, which means we have some really small screens skewing my data a little bit. But what we want to do is let's find the most common screen size. Because screen size is a lot more like a discrete variable, right? You have all of my laptop screens. We only have one, two, three, four, five, six, seven, eight, nine. So there's only nine distinct screen sizes, which again kind of makes sense when you think about buying a laptop. So that's kind of what I mean about being discrete. These are individual values. It's not continuous. I can't buy a laptop with a screen size of 37.51 because it's not a continuous scale here. We got discrete values. So in this case, because we're treating these as categories, and here you got my couple of small laptop screens that are skewing my mean, by the way. But here what we're doing is we're going to grab the most frequent, the mode. The mode's going to be 3962. And same deal, we're going to replace the null value with that 3962. So we did both mean and mode imputation here, with mean being pretty common with numeric and mode being more common with categorical variables.
What,
If
why,
we,
why do they insist on using replace when actually fill NA is the more?
no, I'm not getting into it. Also, I don't do in place equals true anymore either, because this is like they're getting rid of
Or
it soon.
you get this warning now. Yeah, they don't want you to do
Yeah.
that anymore.
Yeah, if you check my notebook that I did when I ran this the other day, you'll see a little bit cleaner code here where
And
that's
also
what I
with
did.
pandas, you can have you can have the
Oh
column dot
yeah.
mode instead of doing what they do.
Yeah, also Pandas has some really good. I'm gonna just grab the fill in a documentation. The fill in a function, it does this for you basically, which is kind of nice. And there's also ways that it can like automatically detect if it should use the mean or the mode too, I think. Anyway, if we have to fix data types, you can use the as type function. Note that that is not needed here as everything is already afloat. But just for example, if you had to convert data types, that is one way to do it. And then if you wanted to fix the column names, you could do that here as well. Basically, you say like df.rename, and I guess my column name was unnamed 0. Yeah, rename that to ID or something. I missed my AI cursor. So there we go. So all I've done here is this isn't in place, but I renamed that column to ID just as an example again. All right, so I like to call that phase one of data wrangling. So this is basic data cleaning. Deal with null values, data types, and column names. Part two is what we call much more feature engineering. So I'm gonna create a new I'm just gonna call this feature engineering. All that feature engineering is making new columns or altering columns from some assortment of other columns, right? How do we combine, transform our columns to create new columns that have meaning? So the couple ways to do this is with all of these tasks here. We'll start with standardization and normalization. So typically, if we're building a model, we want everything to be in the same units. So that's what we're doing with standardization here. We're converting kilograms to pounds and centimeters to inches. Again, probably kind of irrelevant if everything's already in standard units with kilogram and centimeter. But I guess for the sake of example, we're creating a new column called weight pounds, a new feature that is a transform of my weight kilogram column by multiplying it by 2.205. Same thing with screen centimeters. We're creating a new feature. We're engineering a new feature called screen size inches as a transformation of the centimeters column divided by 2.54. So this is a pretty basic way of doing feature engineering. A common one I see that's probably not on units here. I guess it is kind of on units. but like hours to seconds or like minutes to days, um, things like that, dollars to cents. I'm trying to get a more like continuous like no number here. How do I get out of this? This happened last time too. There we go. So this is like transformation of like a simple arithmetic transformation. Data normalization is a lot different. Data normalization typically is what we call something like z-score or scaling, right? Standard scaling. Basically, CPU frequency was kind of a bad example. Let me see if I can find a better one. I'm gonna call it df.describe here. df.describe shows the summary statistics. Actually, there's a fun one too to do like object equals true. I learned this the other day, Karen. I thought this was fun. I can't remember how to do it, but there's a way to do it so it describes like your categorical variable. But anyway, looking at this, you have your mean, median, and percentiles here. So with scaling, you typically look for where there is a large disparity. So I'm actually going to look at the price column. The price column, we go from a minimum of $527 to a maximum of 3,000. So we have a high variance in this feature. And if I actually create a plot of the price column, we'll see that we're kind of all over the place, right? Well, again, this is a bad graph. I don't know why they did that. But anyway, like I want to show the variant. There's high variance here. And maybe if I just call it df.var, I don't know. That's not gonna like that. But either way, the price is a huge variance on it. So with standardization, we basically try and standardize everything within a normal curve. Um, that's kind of what I wanted to plot. I didn't want to plot that. I wanted to plot the values. Um, I guess we have to wait till we do our kernel density plots later. Basically, if I plotted this, it's gonna have a weird skew to it. Basically, we're gonna start with a lot of a low price. I guess we're gonna have a lot of low, and then we're gonna have a strong right tail. So we're gonna be right skewed here. We have some really expensive laptops that are not the normal, that are not the norm. I'm sorry, I've been trying to use Gemini more recently. Make a kind equals KDE. There we go. We'll see if that works. That'll be cool if this works. No, that is dumb. Uh, I'm trying to be extra here. What I get for trying to live code. There we go. Hey, this is what I was trying to draw with my little pen. Was that we're right skewed here on price, right? We have a lot of laptops that cost like $1,000, and then we have a couple laptops that cost like 3,500. So this is a skewed distribution, right? We have right skew on this plot. So what normalization tries to do, it tries to convert this skew into a normal distribution that looks more like a normal bell curve, right? Where we kind of have an equal distribution inside of it. So that's what I was saying. The CPU frequency is kind of a weird example here because if we use the CPU frequency before any normalization, it's already going to be fairly, well, this is also kind of funky. But if I had to draw a real density on this already looks somewhat normal. There's a lot less skew here. You can see that in my values. We only go from 1.25 to 2.75. There's not a lot of variance. It's already somewhat close. So let's actually do both examples here. What we're going to do here is that we're basically dividing the frequency by its max. This is one way of doing a scalar. And so when I do that now, let me actually rerun my graph. still looks kind of funky, and we're just scaled between 0 and 1. So I guess that's kind of not exactly what I was trying to get to here. I want to use the stand. We use the standard scaler later. But anyway, typically what happens with models is that with machine learning models, they hate variance, right? They hate skew, they hate high variance. So being able to standardize and use a scaler, which we're going to get into in the Seattle pricing. When we use a scaler, it typically helps get more signal out of the noise. So I wanted to use a hopefully it lets me do this. Boop, boop, boop. How do I create a new cell? There we go. So all I'm doing here is I'm using a different type of scaler. I'm using kind of our z-score scaler here. And again, if you really want to know what the z-score is, it basically uses the average as well as the variance, or in this case, the standard deviation, to calculate the z-score of it. So that's typically what we talk about with normalization. See if this works. Yay. Lovely. So what we've done here is we've used the Z. I love it when a plan actually comes together. This is what I wanted to learn with normalization. Not like this is a min-max scaler. It kind of works fine. But with the Z-score, notice the difference here. This is on price. So the before was this graph right here, where we're very right skewed, right? With our z-score scalar applied, we're looking a lot more normal, right? Which is good. And our values are less variable, right? We have less variance. We only go from like -5 to 5, as opposed from 500 to 3,500. That's a huge variance. So we've reduced our variance and we've increased our normality. And this usually creates more strong patterns. Again, you're going to hear me use patterns and signal a lot when we talk about machine learning. We want these models to identify strong patterns and signal out of the data, and having less variance and a more normalized data set distribution gives that stronger signal. All right, so this is feature engineering for numeric features. So numeric features are your numbers. We went over two options. The first was just a simple transformation, so transform your numeric feature with arithmetic. And the second was transform your numeric feature using normalization, usually a z-score type scalar. Now let's move on to categories, right? There's two ways to do that I want to talk about here. The first is how do we go numeric to category? And the first option is binning, right? So we're going to create a new feature called a bin or a group that's going to be derived from a number. In this case, they're going off a price, but the thought experiment I want you to do is age. Sure, age is a number, right? It's numeric, 0 to 100, whatever. But whenever you think about reports or demographic information that come in, it's always via age range. So all of a sudden now you have a category 0 to 18, 19 to 29, 30 to 39, 40 to 49, 50 to 59, 60 plus, right? All of a sudden we have a category that represents numbers behind the scenes. That's all binning does. It creates a category that represents a set of numbers. So again, all we're doing here for price is that we're taking price and we're converting it into three buckets: low price, medium price, and high price. And you don't have to, it does that automatically for us. If I look at what these bins are, this is kind of what it came up with. My cheap laptop is 500 to 1500. My medium laptop is 1600 to 2700, and my expensive one is going to be 2700 plus, which goes to the max here of 3800. And again, usually I would say that the bin should be user defined. You should define how you want the bin to be. But in this case, we've gone numeric to category. So yay, feature engineering. And then our last one is going to go from category to number. So in this case, we have a category. We've decided that screen is a category, right? When we looked at it, It had distinct values. Oh yeah, it is a category. We only have two. We either have full HD or IPS panel, right? So this is a category. However, a machine learning model can't just use this as a feature. We always have to have numbers, right? So the way to do this for two categories, this is excessive, but it's whatever. What we're gonna do here is that we're gonna call this pd.getDummies, and let me show you what that does. When we call getDummies, it creates what's known as an indicator variable, which indicates with either true or false or 0, 1. Again, by default, it does it as true, false, which is, again, a machine learning model can't read true, false. It can only read numbers. So we use dtype int to make it a number. So for row 0, it was not full HD, but it did have an IPS panel. So where this gets dangerous, this is also known as one-hot encoding, by the way. Just so we'll get into this deeper in week 7. But where this gets dangerous is, let's say you have a column, you have a category that has 36 values. How many columns is it going to generate if we use one-hot encoding or get dummies on it? It's going to create 36 more columns, right? So all of a sudden you get really, really wide data frames or really, really wide data sets that are what we're going to call sparse. They're going to be filled with a lot of zeros and ones and stuff in there. There's not a lot of other numbers. And that can be confusing for models to train and learn on, unless they're like neural network type things. So again, just the more information, the wider, the more stuff that's there, the more likely it is that a model is going to find um, like patterns that don't really exist. So a very common thing to do is if I do have a whole lot of categories, to first use binning, where I create a new category called other or miscellaneous or something that contains my like 10 least populated categories. And I just group them all under that one bin. So that way that can reduce me from 36 categories to maybe like 15. Pretty without losing much signal. Again, one other thing you'll see in models, again, a lot of this is common sense when you think about it. When it comes down to patterns, sample size matters. If I have a data frame of 200 laptops and only two of them were made in China, is being made in China going to be a predictive feature? No, right? If I only have two laptops, there's not going to be a strong signal in predicting wider laptop price just because of that one many low manufacturer. So sample size matters. So that's kind of why bundling things up to only keep your key categories can matter a lot here. Looking at these counts, I think these both look great, right? 161 and 77. But what's the other one? Manufacturer. I may not have time to do the. Yes, for manufacturer, right? If I look at Razer, they only made one laptop. So is knowing Razer as a manufacturer, is having that little one, the only one for Razer, is that going to be predictive? No. So looking at this, I would probably bundle up all of these into an other category. And if I was feeling really hardcore, I would probably bundle all of these up and just keep the big ones, Dell, Lenovo, HP. There's much more trustworthy signal coming from a larger sample size than from a smaller one. This also comes to the art of making a model. This is a choice you have to make. Do you want to bundle up just these guys, or do you want to bundle up all of these guys? And that's going to create a separate feature, but it's going to create a new model. And that's kind of where the beauty of kind of model engineering and data science actually being a hypothesis comes into play. Like, do it, try both ways and see which model performs the best, right? That's the only kind of way to push forward. Cool. So here we go. We created our dummy variables. And if I look at this, we can see that we have two new columns now, and we got rid of that screen column. So again, our goal is to get all numeric features to train a model. And yeah, if I did that for manufacturer, here's kind of what that would look like as well. Big ideas for data wrangling. Whenever you get a data set, before you use it for EDA or modeling, you need to clean it. To clean it, typically you want to focus on three areas to start. What are your data types? What are your missing values? And what are your columns? So in this case, We did have some missing values. We did have some data types to fix, and we also needed to fix some columns. We reviewed all of that first. Then we dove into, I hate these for this little mailbox. Then we dove into how do we do feature engineering? How do we transform columns with arithmetic? How do we transform columns with normalization? And how do we transform columns with categories or text? How do we do numbers to text? How do we create a category? And how do we go category to numbers using one-hot encoding or label encoding, which we'll get into in a little while, in a few weeks as well. Yeah, your other option, just as a spoiler alert for week 7. The other one, instead of one-hot encoding, it's called label encoding, which is basically just give a number to a text. So a common one is like month of the year, January through December, but those are also written as 1 through 12, right? Same with days of the week, Monday to Sunday, 1 to 7. So that's label encoding. We've gone from January to 1, December to 12. But the problem, and think about it from a machine learn. Computers are dumb. No matter how smart AI gets, computers are dumb. So think about it from a modeling perspective. If I have December as 12 and January as 1, all of a sudden you get this pattern that December is 12 times better than January or 12 times more impactful than January, which may not always be true, right? So there's something to think about. Like that's why we usually prefer one hot encoding. As with zeros and ones, we keep all that bias of the labels out of the model pattern recognition. Cool. I think I only did that one notebook in my last cohort too. So we're gonna pivot over to the house sales, and if I have any spare time, we can look at the EDA one. But I don't care as much about the EDA notebook this week because that's all you're doing next week is EDA. So we're right on time here. James, sorry, and Karina. Oh my God, we knew this would happen. Karen just dipped out. Basically, the United States had daylight savings time happen yesterday, so we ended up jumping an hour into the future. I know, it's terrible. I also like lost sleep, and my poor toddler. Anyway, I'll stay a little bit later to 1:45 on my or
Okay,
12
so hi everyone. What time do the lessons start now?
1 p.m.
Well,
Eastern. And the
that would
problem was
be
all
7 p.m. South African time.
yes.
Okay, cool.
Yeah, let me double. Also, it didn't help when we started this an hour ago that the campus was down. But yeah, if you go, let me see if I can go to the student view here. So if you did go to the campus, not participants, that's the wrong thing. Cool. Switch role to student. If you did go on the campus and you go to the Zoom on here, the live session, I'm hoping it should auto upcoming meetings. Let's say it hopefully should automate like I'm not sure where they are, but it should hopefully automatically convert to your time zone. But yeah, I'll put a big post in. I'll put a big post in Slack about or in the Zoom forum about this because yeah, Karen and I were about to post something and then the campus was down. So yeah, it starts 1 p.m. Eastern to wherever that is in your local time zone now. So maybe an hour ahead. I know some other
Yeah,
countries are daylight saving,
yeah.
like the
In South
UK, I think,
Africa, that would
did.
be an hour ahead
Yeah.
because they don't have daylight savings time.
Oh,
Is
you
this
didn't
going to
miss.
be, sorry, will this now be like continuously like that now? So going forward, it's going to be an hour ahead until we done with the course. Or is it just for
Yes.
tonight?
Yeah,
Unless South Africa jumps ahead with daylight
No,
savings. I don't think it
that's not going to work.
or
Not
Netherlands
needed in South
or
Africa.
Netherlands too,
That's not going
or
to happen.
or if Netherlands does too. I guess
Okay,
they
that's
don't.
good.
I guess
That's
they
good.
don't do time daylight savings time in Netherlands, huh, James?
Okay.
like the UK jumps forward in a couple weeks here. So I know we have a couple folks over there.
Oh, okay.
Yeah. So yeah, we're going off of the Eastern time clock, which maybe we should have done UTC, but we'll put that as a
In
note.
the US, they moved that whole thing ahead a couple of weeks, a number of years ago. It used to be
Yeah.
probably when it was happening. It would be happening in UK now. There used to be start later in the year.
Yeah. And I'll post in chat. And if this time doesn't work for y'all, then let me know. And if we have to push an hour forward, then we could as well. I think like we went by popular demand for this time period at the start of the cohort. So just let us know in the forums. Yeah, just I'll stay a little bit later. I have a hard out in about 45 minutes. But as a quick recap, we went over week 4, databases, history of databases, some of the big ideas I wanted to get covered last week, and then we dove into the purpose of week 5, as well as the deep dive into the data wrangling notebook, and how we can use pandas to start interacting with our data sets before we get into modeling. So for the last 15, 20 minutes here, I do want to focus on the house sales notebook, which should be kind of the final notebook. Let me convert myself back to my normal role. So your keynote activity for week 5, and then we'll cover a couple quiz questions, and then I can review any of this for the folks that joined at the normal time. So let me pull it up. I think it was number 10. I think it's number 10. 5, 10. There we go. So in this last keynote activity here, you're supposed to put all your skills together to import a data set, clean it up, and then build a introduction to linear model or predictive model on top of it. So we'll wait for this to click over on the kernel side. Hopefully it loads the kernel. Be sad if it doesn't. Otherwise, I'll just have to switch back to my other one that I had up. Yeah, this may not be loading. So we'll switch over here. I'm going to load up the same notebook here. Cool. All right, so we're in the House Sales in King County, which is a county in Washington State in the United States, and we're going to be looking at housing prices in Seattle. All right, so we're going to load in some of our libraries here, and then we will fly through some of the data wrangling and then spend a lot of time looking at the linear modeling side. And hopefully this housing CSV works. Cool. So let's load in our data set. Should be this housing.csv. Should be able to read it in. Yay. And we can look at our df.head. All right, so this is kind of what our data frame looks like. Oh, and look at me not doing this live last time. Cool, so let's kind of work through this. First thing we want to do, we have 22 columns here, and we know what we need to check. We need to check for things like the null values, columns, as well as data types. So let's call it df.info. That's going to be the first thing we're going to do here. And looking at my df.info, I actually feel really happy about this. So let's say why is Alexander happy about this? Well, I'm mostly happy about it. So again, we wanted to check 3 things. Data types, null values, and columns. So for data types, as we talked about, models really love numbers. So I have all numbers except for one, which is an object, a string, and its date. So, I'm already getting a red flag. If I have a column called date, it probably should be a date time, not an object. But if we look up, I do see that, yeah, this is a date, and we need to convert it if we want to use it as a feature in our model. But we only have the one, so we only have one bad data type. One bad data type, which is the date column. Next, I'm going to look at null values. For null values, we have 21,613 rows, and every column has full rows except for 2. Bedrooms is missing 13 rows, and bathrooms is missing 10. And I will tell you right now, I do not care about any of those. And I'm going to go back to my rule of thumb here. If I'm missing 13 rows out of 21,613, that is 0.0006%. So we're missing less than 1%. We're missing less than like, yeah, we're way under. We're missing 0.06% of the data, which is not a lot. So I would just drop the rows, drop the NA rows. I'm not going to impute them. It's like not worth the effort to impute them, basically. And then in terms of my column names, all my column names are lowercase, no foreign characters. There's a couple weird ones, like these should probably be latitude and longitude. You could probably spell out year. We probably need to drop this unnamed zero columns, but for the most part, they're not so bad. So yeah, in the real world, I would fix the date-time column. I would drop the NA rows, and I may fix a couple of these column names, but they're not bad to me. We can then use df.describe, and we get our numeric representation of the data sets. Moving into the data wrangling, what it wants us to do, drop the column ID and unnamed zero, and then, I don't know why it wants to do that, but I would probably keep the ID column. So I'm just going to cheat and grab the one that I did earlier in the week. Cool. So the first thing it wants us to do is I would probably keep the ID column just so we keep our unique one. I think they're having us drop it because it's not a predictive feature, right? Knowing the unique ID of a house is not going to help us predict the overall pattern of housing prices in Seattle. So that's why we're dropping the ID column, and the unnamed zero column we don't need either because it's an irrelevant column index here. And so this should give us all of these columns that are left. Next, let's look at the missing values. We already know we're missing 13 and 10. They're doing an imputation here where we're filling them in. Remember, they're grabbing the average bedroom and then filling it in. So quick question, why would be using the mean here not the best course of action? Let's put your thoughts in the chat, especially if you're around for the imputation question. Similar with the screen size. It's a discrete value, right? I have the 1, 2, 3, 4, 5. I have up to 33, so that's a crazy one. But I have a discrete number of bedrooms. If I just look at the mean of the bedrooms, it gives me a decimal number, 3.37. That doesn't really make sense. So if I was doing this again, I would just drop the rows, but I would also replace them with the max value. So maybe that's what we do here. Value counts dot idx max. That should give me 3. So here we go. We're going to be doing 3 bedrooms as my imputation. And then we can do the same thing for bathrooms. Again, I recommend doing the mode of the bathrooms. Similar idea, right? It doesn't make sense to have a decimal value for my bathroom number. And now we got rid of all the null values. Here we could also fix the date time if we wanted to as well, which I'm going to try through AI real fast. That's what I wanted. So if I parsed my date time, let's just fix the date. We should be able to say convert this to a date time. And if I call df.info on this now, we should have a date time for it. And the reason why this is important is if I wanted to do some feature engineering, we totally could, right? So if I wanted to see something like, does the average house price change in the summer versus the winter months? We could totally answer those questions now. We can make a new column called month, df.date.month.dt.month. And that should be able to, look at me coding by myself. And that gives us the month that this listing was put up. So this was listed in October, November, December. And again, going back to what I just taught you in the last notebook, we can now bin these to create seasons, right? Fall, summer, spring, winter, and then use one-hot encoding to get my dummy zeros and ones for those 4 seasons. And now we can use season as a variable in my model, right? So more feature engineering work. So that's kind of why it's important to make sure your date times are correct. I'm not going to bother updating column names, but you can already kind of do that on your own time. So, and so far what we've done with our data wrangling, null values, data types, columns, as well as a little bit of feature engineering. Let's create some plots here because that's not what I want to spend a lot of time on. And if you're just joining us, I didn't spend a lot of time on visualizations this week, mostly because you're going to be doing a lot of visualization next week. So all these same graphs, you're going to be making them all again next week, as well as a bunch of other cool ones. But what I do look for is distributions. So we talked about this in the last notebook as well. But if I'm looking at waterfront, right, I'm seeing a lot of skew in this as well, right? So if we're talking about if something needs to be normalized or not, this can give us an understanding of whether or not the feature needs scaling. And spoiler, almost all columns in all data sets typically need some type of scaling. So here we're making a regression of this is our line of best fit of square foot to price. I don't even like the square foot above. What's the column that we usually use? Square foot living or square foot lot. I'm going to do square foot living here just so you see it. We should have a pretty strong line of best fit here. So when we talk about line of best fit, this is good. This is going to get me into my kind of first idea of a linear model. So let's talk about linear models here. With a linear model, a couple things to note. Linear models are kind of the backbone of predictive analytics. They've been around for hundreds of years. Galileo, Isaac Newton, all the folks back in the day, 1600s, doing their calculus under their apple trees. This was all done with paper and pen. So if they could do it in the 1600s, computers can do it really, really quickly and really, really fast now. So what is a linear regression or a linear model? A linear model is defined by a mathematical equation that you can always sub variables and things into that will result in an output. So for example, a linear regression, we may all know it, y equals mx plus b, right? Take your x, multiply it by m, add b, and you get the output y. And if you graph it, it should draw a nice little line like this with your rise over run or your slope, and then your constant, your constant here would be. These equations get very crazy very quickly. If we have multiple variables, we get an equation that looks like this, where we have y equals m1 x1 plus m2 x2 plus all the way up to how many variables are in your thing, plus your final b. But either way, it's still an equation. And even when you get into crazy things like ridge, which I think we'll do, ridge regression is still an equation. And I don't know my Greek letters anymore, but yeah, it is still an equation. That's all I kind of want to get to the point here. And some of the other ones we'll do, lasso is going to have an equation. Logistic regression is going to have an equation, right? So whenever we talk about linear models, even polynomial, which we did in this week, it's going to have an equation, right? Just know that polynomial starts using exponents, while linear models typically don't use exponents. Either way, it's still an equation. And if it's an equation, it can be done with pencil and paper, and it can be done, and it's very defensible, right? There's only one answer, right? There's no randomness involved. There's only one solution to getting this equation. And there's a whole lot of mathematical proofs behind all of them. So, for example, a linear regression, its mathematical proof is with something called maximum, you don't have to know this, but maximum likelihood estimation, which is kind of a proof for, let's see, proof for linear regression. Let's see if this will come up. Yeah, the book of statistical proofs, if you want some light reading tonight. Uh, given this equation, how do we prove that it works? I had to do this in a little blue book with pencil and proctors back when I was in undergrad a long time ago. So that was a good time. Good time. Anyway, you don't have to know this. What you do have to know as a data science, linear models are defined by equations, which makes them trustworthy and it makes them easy for computers to do, right? So because it's easy, it's descriptive, it's defensible, you can talk about it, and there's only one right answer. If you get an equation, I can go up to a non-technical stakeholder and they can be like, why do you think we're going to sell 50 books tomorrow? I can pull out my little calculator, show them the equation, plug it in, and say, hey, look, my equation spat out the number 50, right? Contrast this now to modern AI models, which are typically known as black box models, which we'll get into in week 7 and 8, which in those cases, how they generate the predictions are not known as well. And there is a lot more randomness involved in that. There is no set equation necessarily to an XGBoost model or a neural network. But with a linear model, there is. So with linear models, these are typically known as the baseline for machine learning. You always start with a linear model. If your more complicated model doesn't beat or outperform a linear model, what are you doing? A linear model is always more explainable, always more trustworthy, and always less computationally expensive than any advanced machine learning algorithm. So that's kind of why we're starting with that here. So for linear regression, it gets automatic, even just with a little Seaborn can fit one in just a plot function, which is crazy. Again, super easy for Model 4 computers to solve. So in this case, we look for features with a high correlation. Features with a high correlation to price include square foot living, as we've just demonstrated, as well as the grade. What's kind of the an independent observer's grade for the quality of the house. But we also see some interesting ones. Latitude has an interesting correlation. So depending on my latitude, my housing price may be different. And that could be maybe like the neighborhood or if it's by the water or something like that. The number of bedrooms and bathrooms, whether it has a good view or not. But we see there's a lot of confounding correlations here. And what I mean by that is if I have a high square foot living, I'm probably also going to have a high square foot basement or lot, right? Or I'm also probably going to have a lot of bathrooms if I have a lot of square foot living, right? So that's something that you have to watch out for. And this is a problem with linear models. Linear models have assumptions. And we all know what happens when you make assumptions. Just kidding. But with linear models, we have problems. And so here are some of the problems with them. And one of them we've already talked about. First is normality, right? We want to make sure that our variables going into the model are normally distributed. That is why we need to use a scalar before we train a model, right? The variable needs to be normal. The second is multi-collinearity. We want to avoid multi-correlations. And so again, if I have a linear regression that has number of bathrooms, square foot of the lot, and square foot of the area, and square foot of the basement, those are all going to be correlated pretty strongly to each other, violating this independence, right? All of my features should be independent of one another. And so again, there's some mathematical ways to get around that, known as like PCA, principal components, which we'll do in a couple weeks. But long story short, these assumptions, they make it really difficult to actually be mathematically sound in a linear model. And when we get into things like random forests and neural networks, they do not have assumptions. So you can freely make one without being yelled at by the math police. And I'll also just caveat this. These assumptions, they're not going to stop you from making a linear model. I know plenty of people that made pretty good models with features that had multicollinearity or that they didn't use a scalar on. And nobody's going to barge down your door and arrest you for like violating the mathematical assumption. That should be kind of funny if they did, though. But what you typically see is that you're likely not maximizing the performance of the model. The linear regression will be stronger in its performance if you do follow these assumptions, right? So adding a scalar is a really quick and easy way to make sure that you meet this normality assumption, right? PCA is a lot more difficult, but being smarter in your feature selection gives you a stronger way of avoiding multicollinearity, right? Like maybe we should add up the square foot of the basement and the square foot above and the square foot living and make a new column called total square foot, feature engineering, arithmetic of columns, and just use that column as my feature. In this case, it's using the longitude here, which is kind of silly, but we can do it. You'll see that the longitude doesn't correlate very well, so we can already tell that this is going to be a bad model. So here we go, and we get an R squared of basically 0. So it means that our model does not explain the target at all. So this is really bad. For R squared, this is going to be a number between 0 and 1. The closer to 1 means the more variance in the target that your model is explaining. Basically, how well does your model predict the target? We'll finish up question 6 here. In this case, we're going to use a real feature called square foot living, and we end up with a score, R squared of 0.49, which is pretty good. And if you're curious, this correlation value, this is my R, or my initial value. And if I square it, it should give me the R squared value. So it's the same one here. So look at that. Math works. 492853. All these other nonsense is just because of rounding issues. But we can see that this does match up. We do have this R squared of 0.49. Again, that's not great. We typically want to have an R squared of between 7 and 9. But we'll see if we can get there. Does it list the equation here on this one? It doesn't. I think it lists the equation on one of the other notebooks. But we'll blast through the rest of these because I wanted to give a little bit of time on the quiz. So in this case, notice that we're using multilinear regression, right? We have multiple features that were being used to predict the target, and we end up with a slightly better score of 0.65. But here's what I wanted to show you. If I look at the correlations of my X, we violate the multicollinearity assumption, and that we do have multicollinearity. For example, bathrooms correlate strongly to the number of floors as well as to the total square footage of the house, which again is to be expected here. So again, no one got mad at us. No one's breaking down my door because I used features with multicollinearity in my regression. But we probably didn't maximize the performance of the model. All right, so to get a little bit further ahead, we're going to use a scalar now to normalize our variable. We're going to have a more advanced regression by adding in exponents using the polynomial. And then we're going to still fit our linear regression off of those exponent polynomial equation. This is known as a pipeline. Pipelines are going to save you a lot of time when we get into downstream. But what I want to show here is we were just with the same data set, right? The same multi-selection. We were really able to quickly, just by scaling it, improve our model performance by applying the normalization and applying a more exotic polynomial, I guess, term. Finally, we can fully evaluate how the model is done. The way we do this is by again, we'll get more into this in week 7 and 8, but we're going to first do what's called a train test split, which means we want to train the model on some data and leave out or hold out some other data set, and then test the model on that unseen data. Think about how these models are working in the real world. In the real world, we deploy a model and we use it to generate live predictions. You drive up to a house in Seattle and you want to immediately know how much it's going to cost you. So you plug it in and you get a prediction out. That is unseen data to the model. So when we evaluate the model, we want to evaluate the model on data it hasn't seen. That way we get more trust in how this model is going to act in the real world. So by withholding a test set we make sure the model is evaluated on data it hasn't seen. So that's what we're doing here. We're holding out 3,000 rows and we're training on 18,000. And again, this is why sample size matters so much. If you don't have enough rows, then you're not going to be able to train good models. So in this case, we withheld 3,000 rows. We're going to try a more exotic linear model known as a ridge model, a ridge regression. Ridge regressions are pretty fun. Again, we'll go more into this in week 8 and week 9. But essentially, what a ridge model does is that it tries to account for the fact that we're all lazy and we don't meet these assumptions. So, what a ridge model is going to do is that if a feature does have multicollinearity and it has less of an impact on the target, it's going to lower or minimize the coefficient. Remember, if our equation, I'm going to be fast here. If our equation is y equals m1 x1 plus m2 x2, right, our price is going to rely heavily on these constants right here. So let's say x1 is square footage and x2 is bathrooms. And I know that they both basically have the same correlation or the same information, the same pattern with price. What a ridge regression is going to do, it's going to identify this and it's going to take the bathroom coefficient and it'll send it close to zero, right? So if it is zero, then the bathrooms don't even matter anymore, which makes sense, right? Because they shouldn't matter because they have multicollinearity and we should just be using square footage anyway. So it's kind of nice that Ridge and another one called Lasso. I think Ridge sends them to zero and Lasso like approaches zero but never does send them to zero. Something like that. They're basically like foolproof ways that you can do a linear regression without having to worry about some of these assumptions. But like anything else, ridge regression does care about scaling. So we probably should have scaled this data before we did it, but whatever. And what we can see here is that our model had a slightly worse performance on the unseen data. But this number gives me more confidence in how our model will work in the real world. So, I probably wouldn't trust this model to give me the price of a house in Seattle, but that's a good representation of how linear models kind of work and how data scientists work with linear models, especially in the scope of these assumptions. Last one here, right at the buzzer. All this order parameters doing is telling us how many exponents to allow. So we're going to go all the way up to a squared feature here. So we're going to train our polynomials and then fit a ridge model off of the polynomials. And this does increase our performance. But one thing to notice here is that the gap between my test performance and my train performance is larger than it was here, right? In this case, it went from 647 to 659. In this case, it went from 70 to 74. So that's a pretty dramatic increase. And what this also implies is that maybe we're overfitting. We have more information in the train. We have patterns in the training data that is noise and not signal, right? And again, we're going to get into all this in week 7 and 8 in way more detail. But it's something to think about as they're starting to evaluate models here. So let me summarize and wrap, and then we'll do some quiz questions for 10 minutes and then call it a lecture. So big idea for week 5. I spent a lot of time on data wrangling because we're not going to touch this again. This is going to be assumed knowledge moving forward. So if there's one thing to focus on, it's data wrangling, data preprocessing, how to clean and prepare data for visualization and modeling, right? With visualization being EDA and modeling being machine learning. We covered a couple big ideas here. The first is how do I deal with null values with imputation and dropping? How do I deal with data types by converting or casting, as we did with the date time there? And then finally, how do we fix our column names just to make sure that our columns are working as needed? Then we went into feature engineering. How do we combine or manipulate existing columns to create new ones? Whether it's arithmetic, where we just multiply dollars to cents or kilograms to pounds, or if it's something more exotic, like scaling data. We also talked about why scaling data is important for machine learning. For those of you that joined a little bit late, we showed how this price column is skewed. We're skewed to the right But after we apply normalization, we're a lot more normal in terms of a bell curve of this column. And as we saw in our assumptions, having normality in my features is going to give me a better performance in terms of linear models. We also discussed how to convert numeric features to categories and then categorical features to numbers using encoding techniques like one-hot encoding and label encoding. Then you had an exploratory data analysis notebook, which I didn't do live, but it's an introduction to the visualizations that you're going to make. And then finally, we brought it all together with building linear models. So big takeaway from what I want you to get across here, linear models, your line of best fit, even if that's all you remember, rise over run, y equals mx plus b, that is machine learning. Linear models is the beginning of predictive modeling and machine learning. We are training a machine to learn patterns in your data set. So with machine learning, there's a couple things to keep in mind. Garbage in, garbage out. If you have garbage data going in, you're going to have a garbage model. That is why pre-processing is so important. Second, we always start with the linear models because they are explainable, they are easy for computers to do, and they always result in an equation, which makes them trustworthy, right? If I have a linear model, it's typically really trustworthy to get an executive stakeholder to buy into it. The problem is that linear models typically don't have robust performance compared to modern algorithms due to the fact that they have these assumptions, they don't capture non-linear effects very well, and they typically are tough to scale on big data architectures in terms of like finding strong signal in them. The more data, the more columns you start throwing at them, the easier it is for them to get confused and find noise potentially. Again, as we kind of saw here. So in this workflow, we fixed our imputations, we fixed our data types, we dropped our columns, we created some new features, we created some graphs, and then we created our model. So once we know we want to create a model, we then go into the model workflow. The model workflow is typically going to be split your data into training data and test data, train the model on one, evaluate on the other, fit the model, and then evaluate the model. We evaluate the model in terms of metrics. For linear models today, we evaluated our metric of R squared, which essentially just dictates the goodness of fit of how much the input variables predict the target. And then you compare all your models, you look for the one with the highest R squared, and you call it a day, usually. That's kind of the workflow we did here. We also introduced the concept of pipelines, which allow us to have multiple steps in one spot where we scale the data, add in polynomial features, and then train the model itself. So pipelines would be an easy way to organize your models when we get into that in week 7 and 8. And then we also touched on exotic linear models like Ridge and Lasso. And if you're really feeling crazy, there's one called Elastic Net, which again are still linear models. They're defined by an equation, but they handle the assumptions of linear models a little bit better, right? So, for example, Elastic Net handles multicollinearity well, right? So again, that's one of the big things here. When we move into more exotic models like random forests and neural networks, they do not have assumptions like linear models, which makes them easier to apply in a broader sense, but they also come with the trade-off of being a lot less explainable and a lot more black box in terms of how they're generating a prediction. Woof. One thing to keep in mind, pre-processing. That's all I really care about this week. Week 6 is all EDA visualization. Week 7 and 8 are all machine learning. So this was an introduction to both visualization and the predictive modeling pieces that we're going to go in depth on over the next 3 weeks. Sweet. Last thing I had, and then 5 minutes. I gotta head out. I want to touch on the week 5 quiz just to make sure there's no crazy gotchas. Am I still on student mode? I hopefully am not. Cool. So let's take the quiz and we'll see how it goes here. What's the following line of code do? Creates a linear regression object. Yes. Notice it does not fit, and it doesn't actually predict anything. D is kind of a weirdly worded one, but I think it's A. What's the maximum value of R squared? I mentioned that on the call. It's 1. What steps does this perform? First, it does a scaling, then it fits a model, and that's all it does, and then makes predictions. So it performs a prediction using a linear regression model. It doesn't do correlations, it doesn't do R squared, and it doesn't do polynomials. This creates a maximum of 2, I think, between 0 and 2 inclusive. I think it's maximum 2. I may be wrong on that one. Consider the following equation. Y is the target. What's the result of this code? Uh, Cross-validation, we didn't really talk about in lecture, but essentially what it does is that, no, I don't have time. We'll talk about it in week 7 and week 8. The average R squared on the test data for each of the folds. But isn't there 3 folds? Karen, I may be wrong on that. Have you taken the quiz yet, Karen? No? Oh, good.
No, not yet, but let me look at it.
I've
I think
done
it's a
it.
couple.
Yeah,
Use
yeah.
the following
All right.
code.
Let me know if I'm off base on any of these. How would you organize the values of 1 to 100 as puzzle as for a grid search? And we'll do grid search in week 7 and week 8 as well, but it should be A.
That's correct.
Number, and we consider from the default sum of the data set, divide a data set, blah, 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 blah. What's the following sum is correct? The 100th order polynomial. That's crazy. You should create another linear model with all the data. You should use a simpler model. You should use your test data to test the model further. So we created 2 models here. One just created 0.5. The other one was overfitting. I think you should use the simpler model. I would say this one is overfitting because it's doing too much. But maybe I'm wrong on that one. What's the purpose of folding your data sets? Folds are used for cross-validation. Essentially, it's like you train the model on different train test splits to try and make sure you have a robust understanding of the model performance. Blue represents the data, orange represents the true function. That's not a bad model, not too crazy. Which of the following is true of the model? The model is displaying overfitting because at the beginning here, it's doing too much. It should just be doing this. So whenever your model is doing too much, it's known as overfitting. Or when it sees patterns that aren't really there. So overfitting is when the model sees patterns that don't exist. So we'll see how we do here. I'm thinking we got 2 wrong.
Oh,
Yeah, we'll see how we do. Oh, we got 3 wrong. Womp womp. Almost
oh,
passed. Correct, well done. There we go. Correct, well done. The correct answer is 2. Nah, whatever. I guess, I don't know. I think it's maximum. Whatever. The predicted value of the test data using cross-validation. There is no test data, though. I don't know. Whatever. Dumb question.
what is there is no predictive.
You should
There's no
use your
test
test
set.
data to test the
Well,
model
there's no
further.
test set because of
I
cross-validation.
know.
You're pulling out a section of the training data for each time around.
Anyway, yeah, dumb questions here. So
Uh,
hopefully none of the right answers. I think you can go off of this instead. So again, I would use the simpler model here as well. But I guess trying to get a better model could be an answer. I get why they're saying this one. I kind of get why they're saying this one. And I kind of get why they're saying it. These are all just kind of dumbly worded ones. Again, just take multiple attempts on this to get the grade that you want. And don't worry too much about it. All right, I gotta hop here. I got a hard out at 1:45 my time. And yeah, for the rest of that jumped on, so we're gonna be going an hour earlier than normal, just while the daylight savings going. And if that doesn't work, then just let me know and I can reach out to the people who kind of did this. Again, it was all of you that made that updated the time before the class started. So you all have the power. We're here for you all. And I'll make sure to communicate all this in the forums as well. This recording will be up. If you did miss the first hour, go back and watch it on your own time. And I will see you all next week. Thanks, everyone.